Hello, my name is Kumara Venkata, and this is my final project for the MQTT-based privacy communication system. So the project is titled Securing Privacy in MQTT Systems. So the main objective of this project is to simulate the communication between victims and drones, which are acting as brokers, and a command and control system, which we call it as C2, while also identifying and mitigating privacy threats. Hence, in this video I will walk you through and explain about the following. The primary being the problem which we are trying to solve, followed by the threat modeling process using the LINDDUN framework, the system implementation with privacy enhancing technologies, followed by the evaluation of the results and final remarks. The focus is on protecting users' privacy during message transmission in calamity situations. We also use a structured and a technical approach towards solving this problem, and I'll also guide you towards the setup of the whole environment which I used, including the codes of the publisher and the subscriber model. I will also show you how to install the Mosquitto framework in Linux, and also the Mosquitto clients which we use to communicate between the C2 system and the drone. And this is my introduction, and now we will go to stage 2, which is privacy, which is using LINDDUN framework for privacy threat analysis. So coming towards the LINDDUN framework, we let's begin by examining the privacy threats using LINDDUN framework. So here LINDDUN basically helps us to categorize privacy risks into 7 types. Like the name suggests, in LINDDUN, L stands for linkability, I stands for identifiability, N stands for non-repudiation, D stands for detectability, and the other D stands for disclosure of information, U stands for unawareness, and N stands for non-compliance. So I'll also show you here is the data flow diagram of our system. It includes the victim device, which we use it as the publisher, and we also have the MQTT broker, which is also the drone. We also have the command and control center as our subscriber right here, and we also have data stores like message queue, transient message queue, and identity token store. And these components are inside a trust boundary because they have a trust on themselves, and no outside information can seep through it. And inside this trust boundary we also have another boundary which has the MQTT client, which is the paho-mqtt, which sends an encrypted MQTT payload to the drone, which is the MQTT broker, and these are inside their own trust boundary because the channel is encrypted. Now let's go through some threats. So if we take an example of linkability, so we have a threat where the same user can send messages over the same topic and they can be tracked easily. For example, if the client sends a message to the broker without using encryption and by using the same headers, we can easily intercept and modify the message without the broker even knowing it. If we consider the case of identifiability, the victim's name or the GPS location can be shared in plain text, which is highly not advisable because It can be used to easily identify the location of the drone, which is not at all recommended. Coming towards non-repudiation, sometimes the user cannot deny sending messages with their name attached, because as the drone needs to know the metadata from where it received the message, and the user cannot simply write their name in plain text. Coming towards detectability, we have to check whether the message is encrypted or not, because if not, then the messages will be still available on the network since it is in plain text. If we consider the case of disclosure, like without encryption, sensitive info like medical needs, medical supply list, and all other important information can be leaked and can be read easily by any attacker. Coming to the case of unawareness, the victims don't even know how their data is used, so we need to be transparent with the users, and we need to disclose all our the policies and stuff, so that the victims might understand what we really meant to do with their information. Coming towards non-compliance, like no consent, access control, or encryption used, these three might result in a very huge mistake if followed, because no consent means it directly reduces the chance of following important international policies regarding privacy, and access control because only people with access has to get information that is really meant for them, and lack of encryption, because encryption is very necessary in situations like these. So these help me to decide which PETs would be most effective. So PET stands for privacy enhancing technologies. So let's go through the code and also the environment setup right now. So in this part, I'll show you how to set up an environment in your system to view and execute the code which I implemented. So here I'm using Linux Mint. It's based off Debian. So you can see I'm using Linux Mint 22 as my OS, and I'm using it in VirtualBox with the Linux kernel, and I'm using a bash shell. So this is the details of my machine. You can also use Ubuntu or Seed VMs Lab. Anything can work as long as it's Debian. So now you just open your terminal, and you just have to update the whole system. It's sudo apt update, and type in your root password, and then you can see it updated all your repositories. Now we have to upgrade the system to the latest version. So you can see I have already did the upgrades, so there's nothing left. So we are on the latest build. Now we have to install the Mosquitto framework using sudo apt install Mosquitto, and this will install the Mosquitto framework in your virtual machine, in your Mint machine. Next we also have to install the Mosquitto client. So you can see it's already installed, and it's the newest version. So these both are installed, and if it's your first time doing the install, it will ask you a prompt to type whether you want it to be installed, like a confirmation. So you have to type Y and press enter. That's it. Then it will install it to your system. So next, to also view the code better, I installed VS Code. It's like an open source version of VS Code right here. So you can install it using the Synaptic software manager, and so here is the main UI. It is similar to VS Code, but it's open source. So here you can see I created two files, the publisher.py and the publisher2.py. So publisher is the initial code which I didn't implement any PETs to it. So this is the first code which I worked on. There is no privacy enhancing technology in this code. It's like a basic bare bone working code. And even the subscriber.py, it's like the bare bones code for the subscriber. You can see I didn't use any PET technology here. I just imported the paho-mqtt client and JSON. So now I'll guide you towards installing the virtual environment to make it work. So go to your terminal, navigate to your project directory. Now do an ls. So you can see we're in the project directory. Here you have to type python -m venv to create a new virtual environment. I already have mine here, so I'm not doing it again. So after you execute this command, you can see a directory will be created with the name env, and it has all the libraries and the Python binaries to only isolated to this working directory. So after creating your virtual environment, you can just use source and just observe here beside my name. So there is nothing here, right? So as soon as I enter this command, we'll go to source env bin and activate. You can see there is env printing on the screen. So this flag is to make sure that we are in the virtual environment and not the local environment. So here I can directly install pip install paho-mqtt. You can see I already installed it. Next we also have to install cryptography, which will come in handy later. So I already installed it, and that's it. So there is another package called hashlib. It's already a built-in default package, so there's nothing from pip to install it, as you can see here. So I'll open a new tab in the terminal, and I'll also make sure we are in the virtual environment right here. So first let me start the Mosquitto framework by opening another tab. Here I'll type Mosquitto. So you can see Mosquitto is already in use and it's running. So now I can do python subscriber.py and here I can use python python publisher.py. So you can see it says published with the JSON file with the name Alice, location some zone 3, message need water and medical aid. Wait, I'll just expand this screen. Oh, I'm sorry. So you can see it's getting published like every 5 seconds, because in the code I have kept a time.sleep of 5. So in the subscriber.py file you can see it says received message from the victim with the name Alice, location zone 3, and you can verify this because in the subscriber code there is nothing which states the victim's name, its zone or the message. There is only the the broker, which is the drone, and the port and the topic. So I can successfully verify that the message is getting sent from publisher.py to subscriber.py using these std outputs. So I'll just stop it by pressing Ctrl C to stop the whole program, and I'll just clear the screen, and even this one. So now I'll just explain the code, the publisher.py code. So I simply imported the MQTT client from the paho-mqtt library. I also imported time so that I can have a delay between each message, not to make it clutter. I also imported the JSON library to work with the JSON file, like the JSON victim data. So I took a variable with the name broker and assigned it localhost because I'm working on my local machine right now, and the port I just chose 1883, and I put a topic of calamity/help, and now I created an object called client which imports the MQTT's client class. So to this object I am passing a method of connect, which will connect to the broker, localhost, and the port. So I also created a JSON variable called victim data, which contains the name Alice, her location, which is zone 3, and the message like I need water and medical aid and some like anything. So I created like an infinite loop by using while true, which keeps on iterating until we press Ctrl C. So here in the payload variable, I can dumped the whole victim's data in the payload variable, so it gets converted into a string. And now using the client object, I can easily publish the payload with the topic calamity help. Now I simply print the confirmation message that the client has successfully published the topic along with the payload, which is the victim's data, in a string. And after it publishes the message, the system sleeps for 5 seconds before sending the next message. So if you go to subscriber.py, I did the same imports apart from time because it doesn't need to sleep as long as it receives the message from the publisher. Here you can say use the same broker like localhost and the same port and the same topic. But here I created two like functions, which is on connect and on message. So on connect will simply try to connect with the publisher using the broker and the port, and upon successfully connecting it throws a message in the terminal saying that connected with a code like result code. And you can see we use the subscribe method from the client library. So coming to the next function, which is on message. So as soon as this function receives a message from the publisher.py, it simply loads the JSON file, which is in string. So the string will get converted into a JSON and will be stored in the data variable, and it will simply print the data variable onto the terminal. So these are like we already discussed in the publisher.py. I simply used client variable again from importing the client class, and we simply call those functions like client.on and client on message. And here we try to connect to the publisher.py using the same broker and port, and we loop it forever because it has to listen to the publisher forever until we press Ctrl C. So this is how the publisher.py and subscriber.py works, and this is without implementing any privacy enhancing technologies. So here like anyone any attacker can be like the man in the middle, and he can simply read the data in plain text. And also to uniquely identify the victim, we used her real name, which is like highly dangerous to use in real life. So in the next part I will implement two privacy enhancing technologies for the same code, and I'll explain how I implemented it and why it is like useful and how it helps the whole system. So in this part I will explain about how I implemented the two PETs in the both publisher and the subscriber files. So here you can see I also left few comments so that it would be easy for anyone who is looking at the code to understand. So in the coming to the publisher code, initially I installed the cryptography framework, which I can show you right now. So if I do a pip freeze, you can see I installed the cryptography framework like library in my environment, and I also imported hashlib, which allows for pseudonymization. So I'll explain everything now. So initially going towards the setup, everything is the same as before. We have the broker which is on localhost, and the port which is 1883, and the topic calamity help. I also created an object from the MQTT client library with the name client, and I also want to connect it to the broker and the port. So now we'll generate a key using the fernet method from the cryptography.fernet library, and I use the fernet.generate key to create a key which is stored in the key variable, and I used a cipher variable to simply hash it with a cipher. So I use fernet of the key. So now we'll open the aes.key file as write bytes, and we'll write the data of the key variable inside the file. So coming to the pseudonymization, we use the SHA-256 to simply hash the hash the name of the user, which is Alice. We also have a salt, so that even if the name Alice is shared by like 2 or 3 other users, using the salt it would still result in a unique hash code. So since the real name is Alice, we use a salt. I just simply typed calamity drone project 2025, and in the hash ID you can see I imported the hashlib.sha256, and in it I simply combined the salt with the real name, and I encoded it, and also I did a hex digest so that it would salt the name Alice with the real hash. So if we go to the payload, it's the same as before. We use the victim data as our variable name. We have a JSON file, and in the ID, in place of Alice, we simply put the hashed ID, and the location as zone 3, the message as the same. So here I also have the while loop, like a infinite loop, which has the JSON payload variable that dumps the victim's data like this payload in string, and I also used AES to encrypt encrypted payload, and I used cipher.encrypt function to encrypt the JSON payload variable, and I published the topic, which is the calamity/help, along with the encrypted payload to the subscriber module, and then I get a published encrypted message as if everything is done successfully, and the code sleeps for 5 seconds before the next message gets published. So this is how the publisher code works now. I implemented two PETs. One is the pseudonymization using SHA-256 and hashlib, and another is using cryptography to encrypt it in AES 256 algorithm. So, and also wait, the example of the generated key, which the key which gets generated from this line of code is this one, like the AES.key. So it's a long key. So coming towards subscriber code, it's the same as before. I just imported paho client, and I also imported cryptography to decrypt the message. I also have JSON, and the setup is same as before. We have the broker, which is localhost, running on port 1883 with the same topic. And here with open aes.key, the key file as read bytes instead of write, we simply read the content of the file and we create a fernet object using the name cipher. Now we have the same two functions as before. We have onConnect, which simply like connects back to the publisher, and if we successfully connect back, it simply prints out the connected with the result code message on the terminal. Coming to on message, so I simply put two exception blocks, like it tries to decrypt the payload first using cipher.decrypt and the message.payload, and if it successfully decrypts it, it simply loads it to the JSON variable, so the string will be converted into a real JSON file and it will store it in the data variable. And if everything works, then it simply prints the data variable onto the screen with the location and the message. It's neatly formatted here. And if we encounter any error, like if the attacker sends his own key instead of the instead of Alice, so we cannot decrypt his key because we don't have his AES file, so we simply throw an error saying decryption failed. And this is same as before, like in the previous code, we just run the code forever to get a receive message from the publisher. So now I'll try to execute it. So first I will do the publisher 2.py. Okay, it's running right now. And now Python subscriber 2.py. Okay, it says connected. Oh, you can see received with the ID. So this is the ID of Alice, like with the salt. Oh, I'll expand that terminal window. Oops. So here's the publisher code. It says published encrypted message like every 5 seconds, and it's receiving the encrypted message here. And you can verify this because in the subscriber.py file there is no like the hash or the name of the like the name Alice anywhere in the code. It's simply receiving it from the publisher via the MQTT broker, which is running in the background. So this is how I implemented two PETs, like privacy enhancing technologies, in the code. So I'll just stop this code right now using Ctrl+C and Ctrl+C again. So this is how I implemented like two PETs inside of the publisher and the subscriber code again. So the difference is that I simply used AES 256 and I used pseudonymization using like from hashlib to simply give it a unique ID instead of real name. And in the subscriber function, I simply decrypt the message using the publisher's public key, which is the AES.key, and using his public key we can simply decrypt the message. And this is how we can do the secure communication between the publisher and the subscriber. And this also makes the messages unlinkable, and it removes all the identifiers that can use to identify the people which are sending or receiving the messages. And using AES encryption in Fernet, it basically encrypts the entire message payload, like this entire JSON file, which we call it as payload. It prevents the disclosure from the LINDDUN framework. Even if the message is intercepted, the attacker can only see the hashed ID, like this one, instead of the real name. So this allows for added security and privacy while using our system during any natural calamities. So the main difference between This and the one I showed you earlier is that in the earlier code, like the victim's data is completely visible in plain text. The broker can read, forward or log messages, and there are also like high risks for identifiability and disclosure. Like everything is plain text and simple. So like coming to like the system with PETs, we can see only the hashed ID is used currently, and the entire payload is encrypted, and also the subscriber decrypts and parses the message securely on its own. And due to the addition of Python's exception handlers, we can simply use them to find out whether the data which the subscriber receives is really from the publisher, whether it's valid, or from an attacker which is invalid. So this is how the whole system works right now with like adding the PETs. Next I'll talk about the analysis of results which I got. At last I'll simply like share the results with you, and also share the differences which I got before implementing the PETs and after implementing the PETs. I'll go through each of it clearly, and I'll explain you. So first let's go to the before and after table about the privacy impact. Oops, I'm sorry. Yeah, so here we have like certain aspects. Like initially, if we take the aspect of ID field, so like before, when there are no PETs involved, the name parameter is simply the real name of the victim, which is Alice. And after we implement the PETs, we can see the name got replaced by an ID, a unique ID, which is a hashed pseudonym. So and coming to message visibility, we can see that the payload is completely readable JSON format, which is in plain text. And after we implement the PET, we can see that the payload is encrypted with AES and the content is completely hidden. Now if we also focus on the linkability risk, we can see it's very high if we don't use any PET models, because the same name is reused every time. And after we use the PET, we can see the linkability risk is low because the ID is hashed and also it's untraceable. So coming towards the disclosure risk, we can see like absence of any PETs can leave a very high disclosure risk, because medical needs and the location is completely visible in plain text. But after like implementing AES encryption, we can see the disclosure risk is pretty low, because there is the payload is completely encrypted. And focusing on detectability, we can see that the message frequency is completely visible. So it's like the band is in the medium band. And now after implementing, it's completely same, because the encryption doesn't hide the message metadata. Coming to debuggability, since there is like everything is in plain text, is pretty easy to debug. And like after we implement with PETs, it's like difficult, because like the IDs are too long to remember, and it's very difficult to differentiate between different messages and different payloads. So focusing on privacy compliance, we can see it's completely poor, because it offers no anonymization or encryption. But after we use AES and pseudonymization, we can see the privacy compliance is very strong, because it offers anonymization and a complete privacy for the user. So this is the before and after table, focusing on the privacy impact. Now if we focus on the system metrics comparison, so there are several metrics which I have found, initially being the payload size, followed by message send time in milliseconds, and the processing overhead in percentage, and the privacy score, which is completely qualitative. So coming to payload size, without using PETs, we get around 110 bytes. Like the JSON is like 110 bytes on average, and with using PETs we are getting 245 bytes, which is like an increase of 135 bytes, which is pretty low compared to other messages, because like at the end of the day we are talking about bytes which can be easily worked on by very like low resources systems and stuff. So coming towards the message send time, we can see without using PETs, it's like the message gets sent in 10 milliseconds on average, which is pretty fast. And after implementing PETs, we get a delay of 5 milliseconds, so it takes around 15 milliseconds on average, because it takes time to encrypt the message and apply hash functions and send it to the subscriber, and the subscriber in turn has to decrypt the message. So there is like 5 millisecond of workload which involves in the message send time. And coming towards the processing overhead, so we can see there is not much processing overhead like in the normal code, like without implementing PETs, because it's just simply plain text and it's forwarding the plain text from the publisher to subscriber. But if we consider the case with PETs, there's around 20% of processing overhead because of all the additional functions that were involved, and the change is like a bit moderate but not too heavy. If we concentrate on the privacy score, we get around 2 out of 5 without using PETs, because there is no encryption involved and there is no pseudonymization. But with using PETs, we get a solid 4.5 out of 5. Because we don't get a complete 5, because even the message should be like even the metadata is not encrypted. So metadata cannot be encrypted, because if the metadata is encrypted, we cannot determine like where we received the message from, and it's a complete loss. So but with using PETs, we got a solid 4.5, which is like a very good improvement over 2.5 without using PETs. So all these results were made using Python's time.time time library, and they are compared in relation to time around the publish and decrypt functions. And coming towards the complete overview, I can say that by applying SHA-256 pseudonymization and AES encryption, this MQTT response system is now better and protects the victim's privacy too. The identifiability and linkability risks have been eliminated through consistent and irreversible hashing and using salts, so that even if the victims have the same name, if there are duplicate names, we get a unique hash every time. And these privacy improvements come with minor trade-offs, like slightly increased message sizes, a small processing overhead like we seen before. But the benefits, especially in these emergency conditions, is where trust is critical. So even if the overheads is pretty low, this PETs implemented will align with the system with modern privacy principles such as data minimization, unlinkability and confidentiality, which ensures the compliance and users' trust. So coming towards the final remarks, so I can say that this project has been an eye-opening exercise in integrating privacy by design into a real-time messaging system like MQTT Mosquitto. So it is commonly used in IoT and emergency situations where speed and efficiency are critical. So the goal from the beginning was to simulate communication in a disaster setting where victims might need to transmit urgent messages containing highly sensitive information such as names, like their exact GPS location and the medical needs. In these high-risk scenarios, ensuring privacy is not a normal exercise, but it's a matter of personal safety and ethical responsibility. I initially started this by modeling the system using a detailed data flow diagram which I showed you earlier, and I applied the LINDDUN framework to identify potential privacy threats. This also revealed that our system in its completely ordinary form was very vulnerable to multiple issues, including linkability, identifiability, disclosure of information, and unawareness. For example, if we take a user's repeated emergency messages using the same topic and name, they can be easily tracked, or else they can be easily read by an attacker. Even worse, without encryption, and the content could be easily read by anyone who has the access to the MQTT network in simple plain text. Based on this threat model, I selected two privacy enhancing technologies, which is the first being pseudonymization using SHA-256 and the payload encryption using AES encryption. This SHA-256 replaced personally identified names such as Alice and stuff with the hashed tokens, ensuring that the messages could not be easily linked back to specific individual. This encryption ensured that even if the data was intercepted by an attacker, it would be unreadable, since it's already been hashed and encrypted to any attacker who is sniffing on the same network. So after implementing these protections, I then observed some increase in message size, the payload size getting increased, and the message processing time, which had an increase of 5 milliseconds. But these are the trade-offs which we have to accept, because in most real-world systems, security is given much more importance than the overheads. So this showed me that even in resource-constrained environments like MQTT, it is entirely feasible to introduce strong privacy measures without breaking functionality. Most importantly, this project helped me to understand that privacy engineering isn't about choosing the right algorithm. It is about aligning our technology with human trust and legal requirements. Tools like ThreatDragon had helped me a lot to design the DFT needed for this system. I used LINDDUN threat framework to guide me about all the threats which the attacker might do on the system. And in conclusion, I have included all the source code, the configuration files, and the documentation in my GitHub repository, and this video will be uploaded to YouTube for everyone to watch. I will include the link to my GitHub repository in the description below. I hope this project serves as a small but meaningful demonstration of how I intend to protect privacy even in challenging communication environments like in calamities or any national disasters. So I thank you all for watching, and I look forward for any feedback or suggestions you might have. Thank you.